Hello, and welcome to my demonstration of my real-world logic block. This design is based heavily on the scrap mechanic logic block, which I have spinning in the background here. You can see that it is modeled fully, completely 3D printed. It actually works. It does require some external circuitry, but this mess isn't actually as bad as it seems. It has a big indicator on the top, along with the side indicator that is showcased right there. And it actually works. This mimics all logic block functionalities, the type of logic block, the operation that it performs, that being AND, OR, XOR, NAND, NOR, and XNOR, can be chosen via these switches on the side, and I will show you that in a moment. This logic block can accept up to 5 inputs, 4 of which are on the side, 1 of which is that top input there, and it outputs a single bit of information, on or off, which is given by that bottom port. These plug together using this 3.5mm port, or jack. They just plug in like this. This is hard to do with a single hand. They just plug in like that, and they're good to go. So this is the logic block plugged into itself. It's a very simple system. Logic block doesn't do logic on its own. It needs some external circuitry, as mentioned before. Specifically, it needs this Arduino and this female header to plug into it. This provides both power to the logic block and the logic that the logic block actually works off of. It's very simple to plug in. So if we go to the back, we'll see that we have this weird battery pile thing that's actually represented in the model. I'm not sure what it's meant to be, but it's very helpful for me. I can just take it out, and then I can take this port and plug it in. Yeah. Then I can put this connector back on to go back to mimicking the model. This logic block is now hooked up. Connection is solely to make the logic block function. If we want to actually do things with it, we need to use these circular ports on the side, along with these extra two. To do that, we just take another of our connectors. This is actually hooked up to a button, and then we just plug it into the logic block, like that, into one of its inputs. You can see that we have this one button with a yellow LED to indicate if it's on or off, like this, plumbed into one of the inputs of the logic block. The logic block is currently set up to be an AND gate. When there's only one connection, that means that it effectively acts as a buffer. That means if the button is pressed, the logic block will turn on. If the button is not pressed, as it currently is, the logic block will be off. You can see that right now. When I press the button, it turns on. When I release the button, it turns off. Now, let's make this actually do a logical operation. I happen to have a second button here with a red LED connected with it. So, if I connect that to one of the other inputs, it doesn't matter which input, it can be any, the logic block will automatically detect that it has a second input, and it will only turn on when both of these inputs are on. So you can see when only one of them are on, or only 0 of them are on, nothing happens, but when they're both on, the logic block turns on, and as soon as I release one, it turns off. Now, you may be wondering how to change the operation that this logic block carries out. And it's very simple. Just go to the side that has all these fake memory cards in them. They currently do nothing. Locate the switches at the top. These switches make a binary number, going from left to right. So the leftmost switch represents the number 4, middle switch represents the number 2, the rightmost switch represents the number 1. Add all these together to get the operation that the logic block is currently carrying out. The number 1 represents an AND operation, like in the game. The number 2 represents an OR. The number 3 represents an XOR, exclusive OR. The number 4 represents a NAND, not AND. The number 5 represents a NOR, not OR. And the number 6 represents an exclusive not OR. XNOR. Numbers 0 and 7 are unused. 0 is unused due to technical limitations, and 7 is unused as there are only 6 operations to be carried out. Another fun operation that this logic block can perform is the NOT operation. Technically, there isn't a NOT gate built into it, but we can use the NOR gate to emulate this. To do this, we go to the side and input the number 5, as that represents the NOT gate. Then, we take one of our buttons and plug it in to one of the inputs. You can see the button is currently not pressed, and the logic gate is currently on, as you can tell by the indicator. When I press this button, the logic gate turns off. When I release it, the logic gate turns on. Off, on, off, on. That's enough of the boring operations that this logic block can carry out. Things really get interesting when you take into account the output of this logic block, once again represented by this bottom port right here. The reason this makes things interesting is the logic block is now able to react to its previous input. You can see if I take a cable and plug it into the output, then I take the other end of the cable and plug it into one of its inputs. Again, it doesn't matter which input, just that some input is plugged in. And then if I change this to a NOT gate, you can see the logic block will flash. The reason this happens is, well, let's assume that we're in the steady state. Let's assume that the logic block is off. When the logic block is off, its output, or its input will be off, because that's its only input. That means that it will invert that input, since it's currently acting as a NOT gate. The inverse of off is on, so the logic block turns on, meaning its only input is on, because that's its, yeah. Therefore, the logic gate will turn off, because the inverse of on is off. This cycle repeats, once every tick. Now, in the game, logic gates run at 40 Hz. Therefore, this clock is a 20 Hz clock. It takes 2 ticks for this logic gate to complete one cycle of its clock. 1 tick to turn on, 1 tick to turn off. Thus, we have a 20 Hz clock in real life, out of a simple logic gate. This concept can be expanded further by adding a button. Because this is a NOR gate in reality, if we plug this in, nothing will happen. But then, once we press this button, the gate turns off. That's because we have a constant on signal into this NOR gate. If we OR anything and 1, we get a 1, which is then inverted to create a 0. Thus, the gate turns off. If I release this button, it's like the button isn't even there, and the clock starts up again. You can see it's flashing, not flashing, flashing, not flashing. We can modify this behavior a bit by changing this from a NOR gate to a NAND gate by giving it the number 4. This has the exact opposite operation of a NOR gate. Whenever the button isn't pressed, the gate stays on. Whenever the button is pressed, the gate starts flashing. Again, we still have this. we still have the output feeding back into the input, which makes it interesting. I can release the button now, and the gate stays on. If I press the button, the gate flashes. This is just a clock again. It's just inverted. Final interesting thing I have to show you with this logic gate is creating a bit of memory. This logic gate can store 1 bit of information. We can do this by changing it to an XOR gate. That is the number 3. So I will change these switches to the number 3. Now, whenever I press the button, the logic gate flashes. But watch this. If I give it a 1 tick pulse, the logic gate swaps state, and you can see it stays like that. If I give it one more 1 tick pulse, it's hard to do, it swaps state again. As you can see, it's fairly hard to do because it's a 40 Hz clock and my hand-eye coordination is terrible, but you can see the concept is there. If you can provide a 1 tick pulse to this logic gate, it will swap state. If you hold it down, that's like giving it a 1 tick pulse every tick, which makes it constantly swap state, which makes it flash. The reason this works is that an XOR gate outputs a 1 if an odd number of inputs are on, and a 0 if an even number of inputs are on. Currently, the output is on, therefore we must have an odd number of inputs on. Our button isn't pressed, so that doesn't count, but our logic gate is feeding into itself, therefore it has one logic high input, one input. Therefore it's high. Whenever if I press this button and make a 1-tick pulse, now you can see that we have 0 odd input signals. The output is 0, and the button input is 0. Therefore, this is 0. Whenever we give a 1-tick pulse to this logic block, that creates a temporary upset. That means the number of inputs changes from even to odd. Therefore, the state of the output changes. Therefore, the state of the input in the next tick changes. Therefore, our logic block will change state. You might be wondering, why in the world does this exist? What's the point of it? Why don't we just use a real logic gate that actually exists in real life? Well, this logic gate has a few advantages. For one, it is super easy to use. You just take this very simple cord, you plug it in. This is easier to do one-handed or two-handed. You plug it in, then you just plug this into wherever you want, and you've suddenly got a gate with extra ports, with one extra port. It's very easy to extend that. In real life, you'd need multiple gate. You'd need to do some fancy stuff to make this work. Besides that, this gate always runs at 40 Hz, no matter what. There is no analog shenanigans going on with this. The advantage to that is that it makes it very easy to see all those weird phenomena that would actually happen in microseconds. Here we can see it happening in milliseconds in the real world. We can actually detect the flashing of that gate, whereas with a real logic gate, that would be near invisible to us. We just see a signal that was on. Besides this logic gate has an integrated output display, both on top. This uses a ton of power, and on the side, this uses a small amount of power. This is entirely configurable to change. Additionally, this logic gate is extensible. You saw this cable I made already, which is jankily connected to my Arduino, and you saw it plugged into the back. But you probably also saw this port in the front. This allows me to take another one of these cables and connect this logic block to another logic block. I don't actually have one of those because I ran out of time, and this takes about 10 hours to make. There's a lot of wiring on the inside. It's part of my extensible I/O series, which means that this logic block is not actually performing any logic. It is solely a very fancy interface to this Arduino. The final major advantage that this logic block has is that it is extremely easy to change. Because it's simply an input, we can just tell it which logic block I want it to act as. I can just say, hey, you're an AND block now. Actually, no. You're a NOR gate. Actually, you're an AND gate. Actually, you're an XOR gate. Very simple to change, and I can use the exact same block for everything. I just need to change the configuration of these switches. Of course, this gate does have a slight disadvantage, and that's how huge it is. That's mostly to line up with the game world, but yeah, I don't really have a good excuse for that one. When I take this logic gate apart and remove all the wires and external everything, it becomes this, plus some wood. The main heart of this logic block is this board, the extensible I/O. This board, extensible I/O. This works through the use of two shift registers. This works through the use of two shift registers. The SN74HC595 shift register and SN74HC165 shift register. You can see I have an empty slot that isn't being used. That's just because this board is designed to be able to do a lot. The way this works is I can shift data in through the 595 shift register and shift data out through the 165 shift register. This allows my Arduino over here to push data to this logic block, that being what the output should be, whether the indicator should be on, whether the light on the top should be on, and some other stuff that isn't really important for this video. And it allows the logic block to shift data over to the Arduino about what it wants to do. So that would be 3 bits of information telling it what type of logic block it is, and 5 bits of information being the inputs. So you can see, this logic block can do a lot. There's a ton stuffed into this small-ish package. And I hope you enjoyed. I hope this project encourages you to make something yourself, be it in a fun simulator game, or in the real world, based on a fun simulator game. I hope to make a new video soon, and I hope you enjoy. Bye!